Hi, I'm Deriv'era and the second episode of ConsoleCraft show. Thank you for incredible support of the first episode. This content created just for fun. I don't want to get into legal troubles, so I'm saying that it's not a professional advice and I take no responsibility on how you will use the information provided. Take everything with a grain of salt. All MCUs, including RP2040, have errata documents. These documents contain information about hardware errors and problems specific to certain chips. Typically, these issues aren't fixed because that's an incredibly expensive process and often not worth the effort. Instead, they are simply documented. RP2040 is no exception. SDKs usually help to avoid these problems by handling errors on the software side. This was just a lead on to the fact that my previous video also contained a few mistakes. I mentioned that the display updates are slow because of the blocking operation of data sending to the screen through SPI. I said that CPU and SPI weren't working in parallel, which was causing low FPS. That's wrong. The slowness was due to other reasons, which I discovered only after diving deeper into fast data transfers with RP2040. When chip's system clock runs at frequencies higher than 125 MHz, the SPI and UART clocks are automatically set to 48 MHz. With the SPI configured using a clock divider of 2, the real SPI clock transfer frequency was limited to 24 MHz. Regardless of how fast the system clock was, this was 3 times lower than it should have been. I'll be dealing with it today. Second is my praise for the 2.8-inch display boards I mentioned from AliExpress. I said they have better displays, but it seems it's more of a lottery. After comparing the batch I have to say that 3.2-inch displays actually look better. I also discovered that there are IPS versions available. Mine are TFT. IPS displays should be better, assuming they are truly IPS, so I recommend using them. A friend of mine raised a concern about connecting a LED directly to the MCU pin, as it could potentially damage not only the LEDs, but also the MCU pins. Well, I need that LEDs to scrap them for their legs. I constantly need those tiny legs, so I intentionally sacrifice LEDs from time to time. Yes, I'm a bit of a LED murderer. It's common for MCUs to have pins directly connected to the main power source with high current. When connected directly to the ground, there is a real risk of damaging the pin. However, RP2040 can control pin current, and SDK provides functions to set the desired current for any of the pins. I've never experienced pin deaths while working with STM32, but it's generally good practice to check datasheets and use resistors with anything connected from power to ground. Well, overall, there weren't many incorrections that I'm aware of, at least so far. Now I'm going to build the device. Here are all the parts I'll need. It's easier to work with something assembled than with breadboards. The way I'm doing it now is probably the most accessible method for everyone. In the future, once I've finalized all the hardware, I'll design a PCB that you can order or make at home. I also plan to show how to make PCBs at home, so if you find following assembly process too challenging, you might want to wait a few months until I get to that stage. You might have noticed a new chip among the parts. Not long ago I was taking a shower and thinking about the beauty of digital code when I suddenly realized I had completely forgot about internet connectivity for this project. This hit me after I had already released the first video, and I had a bit of a panic attack. Who would take a device without internet connectivity seriously at the end of 2024? The issue is the remaining pins that we didn't connect in the previous video were reserved for the buttons. The most straightforward solution to this problem is to use a chip from one of the ancient classic logic sets, the 74XX series, which has been around since the 1960s. Yes, it's older than I am, and according to YouTube statistics, older than most of my viewers. While this model dates back 60 years, this particular chip I have is a newer revision, of course. These chips are still in production and widely used. You can buy a pack of them for about $1. They are extremely cheap. SN74HC 165N is 8-bit shift register. It has a parallel input with the serial output, allowing other devices to read the state of 8 inputs using only just 3 lines. It's also chainable, meaning you can read 16, 24 or even 32 inputs with multiple chips, all using a single serial line. There are chips like ESP RP8266 that allow to add internet connectivity via UART interface with just 2 wires for any MCU, including RP2040. So I have freed up the necessary pins for an internet connectivity chip I'll use in the future, enabling us to potentially load games via Wi-Fi or even browse the web with services like FrogFind. It would be amazing to access a game store directly from the device. So let's finally assemble all the parts together. Here is the schematic of the build. I'll include a direct link to it somewhere in the video description. I will also include a direct link to PSD files that you can open in, for example, KRITA. KRITA is a free software and hide specific layers to take a better look on specific connection. First goes the screen, because it's an essential part. I removed the registers of SD card slot from the back just as I did in the previous video, before installation. I also took a picture of the pinout. Both horizontal and vertical orientations of the display work, but I personally prefer horizontal. It's impossible to position the screen perfectly in the center because the visible area is not well centered on the board. I have a feeling the designer of this really hated people who are into symmetry. As I install the display and RP2040, let me address some obvious questions. Is it hard to solder this? Not really, even if you will do it for the first time. I would say it's more time-consuming than difficult. The process itself forgives minor mistakes. I would consider this as a Lego for adults. Can you break something during the assembly? The only risky pin out there is 5 volts one, which could fry something, but it's not in use at least for now, so even if you make a mistake, you can usually correct it. One tool you absolutely need, aside from a soldering iron, is multimeter. It will help you troubleshoot shorts in your connections. And yes, it's possible to accidentally burn the plastic during assembly, but if you're careful, you should be fine. I have shaky hands since my childhood and I'm still okay. How long it takes? Several hours. If you're recording the process on camera, double the time. Would it be easier to use a custom PCB designed for this device? Definitely, a lot easier. Let's hope the world survives long enough for me to make it into reality. After the display and RP2040 are installed, it's time to add the buttons. Before I install the joystick and the main buttons, I will put the top shift buttons to ensure there is enough space for them. I'm not sure if they will get much use, but I imagine there will be games that require as many buttons as possible. Besides, we have 8 inputs available on the new input chip, so why not to use them? I'll put buttons on the top and the speakers on the bottom, because having buttons on the bottom will kill my thumbs while pressing them. If you're left-handed, that's your lucky day, because you can position the stick on the right side and buttons on the left side. Home-built devices are the most user-friendly when it comes to perfectly customizing the controls for your hands. I often struggle with portable consoles because my hands are larger than average. I also want to mention that all the software will be hardware independent, requiring only an ARM CPU to run. Access to device functions will be handled through the OS, allowing for hardware changes like using a larger RP2040 board with more pins or STM32 chips. Some people have asked me about the newer RP2350 because it's faster and has more memory. However, it's currently 5 times more expensive and has fewer board options. But you wouldn't need to change much to use it for this project. Just update the board type and VS Code and it will probably work without any further adjustments. These buttons can't compete with the rubber ones in factory-produced gamepads. They're just okay. It's something I'll consider for future revisions, but without custom PCBs, it's hard to find better alternatives. Custom PCBs would expand the hardware options. As for the stick, I'll use my last PSP stick in my deposit. So after some testing, I have found a way to install it reliably. First, solder short wires, then use black tape to isolate the contacts from the board. Insert wires into the board and solder them in place. Before securing the stick, connect the wires to RP2040 and test the analog input. Once it's confirmed to work, use super glue to fix the stick base to the board and use dead lead legs on 2 holes to bind stick base to the board, but solder them quickly. Overheating the legs too much will melt plastic and metal will go through it. Material of the stick is very fragile in terms of temperature. You need to assemble it really carefully. I like how starting the result is no unexpected movements at all. All the electronic components will be located under the display. This is the first prototype I made in search of potential problems and to make improvements in the second build. You definitely can tell the difference. Initially I placed RP2040 on the right side and it wasn't a good idea. Left side of the display requires a lot of wiring, so it's better to place RP2040 at the left. Regarding wire lengths, they need to be short and of equal length. For clock, MICO and MOCI, physics is a bad cow. Better not to slur when I almost reach the YouTube requirements for monetization. In other words, how you wire the display is crucial for high-speed data transfers. However, since it's a parallel transfer, there are unfortunately limits to the frequency beyond which the display becomes unstable. Adding capacitors between the power supply and ground didn't make a difference when I tested this with the first prototype. The boards luckily have enough capacitors already. In short, capacitors act as buffers to smooth out energy spikes. Termination resistors, on the other hand, are much more effective. They are installed between pins and devices. 50 ohm resistors are usually preferred, but higher values can be better, so above 50 the benefits start to diminish. At a certain point, the resistance makes it too hard for the signal to pass through. So 120 ohms is considering the upper limit in most of the guidelines. Whom am I kidding? There are no guidelines, I just read Wikipedia. I'll be using 75 ohm resistors. Termination resistors help reduce echo noise. Imagine you have robbed a bank and somehow bought an apartment. It's empty. You will hear an echo of your own voice when talk. Termination resistors are like those Eastern European carpets you hang on the walls. They absorb the echoes of electronic signals, stabilizing them. I also will add SPI pull-up by connecting 3 SPI lines to 3.3 through 10k ohm resistors. Or, well, since I don't have any 10k resistors, I will chain two 4.7k ohms resistors together. I have plenty of those. Let's take another look at SN74HC 165N pinout. It's as straightforward as it appears. Connect ground and power to the grounded power of MCU. Clock in H is chip select. Connecting it to ground is fine since triggering the load will reset the chip's state. This way, even if connection lose bit parity at some point, it will get restored. The load or SH/LD pin goes to pin 11, clock to 14 and QH to pin 15. QH is the bit output pin. The inputs are labeled A, B, C, D, E, F, G, H. Those are your button inputs. Imagine the scenario when a button isn't pressed. The pin would be left floating, not connected to anything, picking up random values due to noise. To fix this, the pins need to be pulled to ground through resistors. They must be of a high value. This chip is a crybaby. If it detects even a minor energy spike, it registers it as a 1. I tried 4.7k ohms, for example, but pressing one button caused all buttons to register as pressed. So I used 75k ohms and they work fine. I think the range from 40k to 75k will be alright. Before plugging in the USB, don't forget to test all connections with the multimeter. Let's use the example from the previous video, it should work fine. If it doesn't, it might be due to a bad connection on the pin pads. Double check if the lines are genuinely connected between the display and RP2040. Connection might be weak if flux or solder you used weren't of the good quality. They might create unwanted connections or interference. I usually use something sharp to clean the spaces between pins, a habit I developed after using lower quality soldering materials in the past. Don't forget to connect the SD card slot. There is something important I need to address. Why this setup is unable to compete with, let's say, Game Boy Advance? Well, I'm kind of a perfectionist, and in most cases you probably won't even notice the following issue. I barely notice it myself, but it is there. The display boards we are using don't expose all the pins from the display controller. Specifically, they lack a VSync or vertical synchronization signal. This signal is crucial because it allows to sync the screen updates between frames, helping to eliminate horizontal tearing of moving sprites. It's like CS 1.6 with disabled vertical synchronization.
Terrorists win.
And not only vsync, all synchronization signals are not exposed, and I wasn't able to fix it in software way even if one fix theoretically exists. I had no luck reading any responses from the screen. I don't know how crucial this will be for you, and I hope it doesn't discourage you too much. You're unlikely to notice this in the video because you would need to focus on specific high contrast scenes with horizontal movement on the real device to see the effect. A YouTube video won't really show it because it's a YouTube video. I'm not talking about demo from the previous episode, of course, I'm talking about the moment when we reach maximum FPS. It's a bit frustrating, but not a killer punch for the project. I can live with it. I believe most of my viewers can live with it as well. There aren't many ways to tackle these limitations. There are three options. First, to live with it, that's what I'm going to do. Second is to get information from the display about current scan line number and wait for a specific moment. I wasn't able to succeed in this so far because I failed at reading of the information for some reason. And to be fair, not only me judging by forum posts. Display answers zeros after the request, no reaction. I have a suspicion something may be wrong with MASO on the board side. Maybe it's different for different boards. This topic will need more research with different display boards from my side. Third option is to find other boards with different controllers. Well, I searched, and they all lack required pins to control vsync. This display board seems to be made for very basic DIY, sadly, and better options are more expensive and not that simple to install, so we stuck with it. I think when the cheap version of this device will be fully developed in terms of hardware, I switch to make videos about not so cheap options, where I will solve these issues one way or another. Custom PCBs will make this possible probably, so just be aware, I didn't care until finding out that some people do. Finally, let's dive into setting up fast rendering for our system. First of all, the name. Ship sails based on its name, so it's very important to give names to rendering engines. I will call mine R12. Think of it as our homebrew version of DirectX or OpenGL, optimized specifically for this project. Some people have noticed already I might not be that good with naming. R10 or Red 10 engine was a 3D engine I have created around 3 years ago based on OpenGL 4.2. R11 was DirectX 9.0C engine that didn't see a lot of light of the day of real world, aside of some demos. So R12 is a logical continuation in my lineup and the one that definitely deserves some success. R12 will be hyper optimized to run on 320 on 240 and maybe 400 on 240 resolution displays, excluding support for anything higher. The reason for this is to reduce the memory overhead associated with sprite position and dimensions data. Keeping memory usage as low as possible is our priority here given our limitations. I always can make R13 for higher resolutions. I'll start by writing some basic functions for R12. The most important one is the line fill function, which will fill lines with pixel data to be sent to the display. This is a core idea for low memory impact rendering, using line buffers instead of full screen buffers. We will use two buffers, one to fill a line while the other one is being sent to the display. I'll create a DMA function to handle all screen data transfers including commands. As I mentioned before, DMA is a hardware component that moves data from one location to another. It has source and target addresses, with the ability to increment either after each byte transfer. By default, it increments the source while keeping the target static, which is exactly what we need here, but I will still set up it clearly just to make sure. I'll also adjust the SPI clock divider since the SD card requires a slower clock speed for stability during the initialization phase. All control data transfers will be blocking as it was before. Control data is short and there is not much of it compared to pixel data. I'll also add delays after each transfer because the display is cheap, needs some time to process commands. Without these delays, the display won't process commands properly. It's fine to use 2 microseconds delays, even so the datasheet suggests 3 to 5 microseconds. The second contains 1 million microseconds just for the clarity. RP2040 doesn't just have a single Cortex M0 Plus core, it has dual Cortex M0 Plus cores, labeled as Core 0 and Core 1. So far we have only been using Core 0. Given the gaming purpose of our device, it makes sense to dedicate the entire second core to the rendering process. Maybe also sound in the future. This way we will have Core 0 completely dedicated to game logic, which should be very promising. To use Core 1, I'll need to include the Pico library for Multicore support. I'll bring in the core functions from the header and use a call to run a function on the second core. Also, I'll add Multicore functionality to CMake file. Before running something on the second core, I'll reset the score after the previous operation. In a separate variable rendering in process, I'll track if the second core is done with its task. It's fine to make it a simple variable without mutexes. I've tested it and it works well. Mutexes in C programming are used for managing mutations of complex shared data between threads, but here we don't need that level of complexity. Let's get something visual on the screen using the code I wrote. I'll start with some moving cubes to make sure everything is working. Also, I will add a timer that will count milliseconds in a separate file and start it in the main file. I will save the timestamp from this timer and use the difference to count how many frames we rendered and sent to the screen per each second. This is the way to check FPS. When the difference is over 1000 milliseconds, I will simply print FPS to our debug interface and restart the counting process. Even if the main code is done, we need to reconfigure a few things. In the main file, I'll set the same frequency for peripherals as the CPU is using by a simple function. In config header, I'm going to extremely overclock the CPU. Looks like all RP2040 should work fine at 276 MHz. It's near the top limit. Remember we set the SPI clock divider to 4 for the display. That gives us 69 MHz for SPI and the SD card will run at half that speed. Overclocking like this can in theory degrade the CPU over time, but since we didn't change the core voltage, it shouldn't be too bad. Not like Intel's 14th and 13th gen of CPUs. Another option will be to use 140 MHz CPU clock divided by 2, but that's not pushing the chip to its fullest potential. If the CPU doesn't start at 276 MHz, try lowering it a bit to 272 or 270 MHz. But I think all these CPU pieces are capable to work it out. In IO.C, we need to increase the current of SPI lines. This makes them less prone to the noise. I should mention that so far I haven't found a way to run SPI peripherals at high frequency independently from the system clock. I'm still unsure if it's possible or not, because the only high-speed clock in RP2040 is a system clock, so all high-frequency peripherals must be clocked from it. Both my prototypes tested to work fine at 280 MHz frequencies. Let's check how it works now in real life. You should see moving cubes on the screen. This is the kind of FPS performance you can expect from this setup. It's managing 48 frames per second, not 60 sadly, but there is not much else I can do to improve it with this setup. Well, at least we're running at 276 MHz under the hood. Hopefully we won't have to lower it due to unexpected side effects. That should be enough to handle Doom level graphics. The only limitation will be the amount of RAM. In other words, this thing is a beast. If I drop the clock to 160 MHz with 80 MHz for SPI, it can hit over 50 FPS, but it gets unstable with wires. A PCB might improve that situation, but lowering SPI clock twice sounds really bad. I'm ready to use 48 instead of 55 FPS just to have so much power for different effects. 60 FPS sadly still feels out of reach. For now. Sprites. Let's first talk about the theory of sprites. For this setup we will use only piloted images, but we will handle several types of them. Piloted image means that the sprite data doesn't store the colors directly, instead it holds indexes of colors in a palette. Each sprite will have a pointer to its own color palette, so you can either share a palette across multiple sprites or create individual palettes for each one. There will be three major sprite types. Common sprites will follow the piloted system I just described and will have three subcategories: 8 bits per pixel, 4 bits and 2 bits. 8 bits are able to address 256 colors, 4 bits will be addressing 16 colors at maximum, and 2 bits will be addressing only 4 colors. For instance, full screen image 320 on 240 with 256 colors would consume 76,800 bytes, but with only 16 colors using 4 bits per pixel, it would use only 38,400 bytes, and 2 bits per pixel cuts that further to just 90,200 bytes. Pixel art can do magic in such limitations. Masked sprites utilize 1 bit per pixel, allowing only 2 color variations. Why is it a separate category? Because there is no need to use a palette. Instead, you can directly assign 2 RGB 565 colors for background and foreground, and they will occupy the same 4 bytes as a pointer to a palette. These are perfect for masks, effects or text, especially for text. And the final type is matrix, basically a tilemap. Tile maps let you create large levels by arranging a grid of the same size sprites with many repeating elements. Each cell in the grid contains a number of a sprite. All tiles will also share the same palette. One byte addresses 256 values, so that's the maximum amount of available sprites for one tile map. We will need two buffers of sprites. One will hold what currently is being rendered, second will be filled by the application for the next frame. The maximum amount of sprites in the buffers will be decided by a developer. I managed to squeeze the display sprite structure down to 24 bytes. So for 100 sprites on the screen it would only need 4800 bytes of memory. For a comparison, Sega Mega Drive could display a maximum of 80 sprites with 15 colors per sprite, so we are slightly ahead of Mega Drive's graphics capabilities. We will also require flags or display properties. One of these flags will enable transparency for the zero color, so any pixel with color number 0 won't be drawn. Another useful feature is mirroring on the horizontal and vertical axes, which helps reduce memory usage. A separate topic is figuring out how the hell to convert images to indexed sprites, with the result of C data arrays. The easiest approach for now is to include graphics directly in the code and build them as part of the application, at least for smaller games and overall the near future. And surprisingly, there is no simple solution for this. Both I have in my mind are actually made by me. There are a lot of online services that convert sprites to C arrays with different graphics modes like RGB 565, RGB 888, grayscale variations and some exotic options, but none of them support indexed color conversion. The first option, which I personally prefer, requires a sprite. You can create a fixed color palette from any image, save the palette and use it in a new indexed document. Then just copy-paste the image there and it will become indexed with palette colors. I found a script on the internet that saves images as text data and modified it to save proper C data arrays. It also detects the palette's color count and adjusts the bit density automatically to the smallest possible size. But a sprite isn't free. It's a great software from independent developer, but I can't paywall you or ask to pirate it. What about fully free solutions? A while ago I created a tool for this purpose, but it only works with 8-bit sprites. It takes any image format, detects all possible colors, and reduces the most similar colors until it creates a palette of only 255 colors or less. The zero color is always treated as transparent. You just need to call the app from the console, and as parameters pass all the images you want to convert. This application is Windows only, but it should work on Linux if you compile the open source code available on my GitHub. The ideal solution so would be a serverless HTML page with a script that handles everything and allows to configure the result. It will work on any machine in the browser, require no downloads and simplify the process. If you're interested in seeing this HTML app happen, your likes, subs, shares, comments and overall support inspire me a lot. With some time and effort I could build such a page, since I know well JavaScript anyway. Such a page app would let you to make a sprite in any free software like Piskel, save it as a PNG file and drop it into the script to get C arrays. With a sprite there is just no need to spend time on this, but I understand the importance of free options. And back to R12. I'll clone the project and leave the display barebones in the repo. Both projects will be on GitHub. I'll start coding by focusing on 8-bit sprites. First, I'll need a structure to describe the properties of a sprite on the screen. I'll also create a context to hold the information about the rendering buffers, rendering process, clear color, and various flags. Context will allow multiple R12 instances to exist independently. For example, an operating system could have own instance of it for many overlays with buttons to quiet the application or take screenshots. Screenshots are important. All the buffers must be provided externally. R12 itself shouldn't hold anything. It will help a lot to support portability. I'll define the structures for sprites and rendering data, unions and enums for flags and types, and implement functions for context initialization, sprite queuing, and rendering. Initialization will set up values for the context structures. New frame function now will fulfill its real purpose to switch buffers. The fill line function will go through each sprite in the queue and process those that match the current line by their Y position and height. Depending on the sprite type, it will call the appropriate function to handle rendering. Rendering of sprites is a tricky process. It requires maximum performance, as well as some transformations like mirroring. To optimize, I'll batch pixel processing rather than checking conditions for every single pixel. The easiest use case here will be to have no transparency and no horizontal mirroring. That's the one I implement first. Transparency will require checking if each pixel's color is 0, and skipping it if so. The only difference horizontal mirroring introduces is writing to the buffer in reverse. I'll solve it with usage of negative array indices. It looks questionable and feels odd, but it's functional and works as intended. The line drawing function contains the bare minimum of conditional checks, because it will process a lot of data, really a lot, and it must remain as efficient as possible. The function for adding sprites to the rendering queue first prepares the data. It requires to crop sprites by the screen dimensions as well as handling vertical mirroring. For mirroring, I'll set a data pointer to the end of the cropped image, and I'll set the vertical data shift to be negative. This way, bigger the used line number is, closer the shift will be to the start of the sprite. The only changes to the display sources involve managing of a context pointer. I'll need to propagate it to all the called functions that require it. In the main file, I'll create and initialize a context. I'll also disable the line clearing flag to improve performance, since the program will render full screen images. Line clearing is useful during prototyping or using a solid background color as part of the design. Let's find an image. I enjoy winter and I like horses, so I found a free image featuring horses. In Serbia we have plenty of horses, but not much snow. I'll open it in KRITA, crop and resize to get 320 on 240 resolution. Then in Aseprite I'll copy the image into the new RGBA document. This format is important. Next I'll create a palette from it, make a new indexed image with the same resolution, load the palette and pass the image again. Personally, I'm not satisfied with how Aseprite converts RGB to indexed colors. For better results, you will need to do some manual work with color palette and image itself, but for tutorial, I think it's okay. Finally, I'll use my conversion script to make C-data arrays and save the result in our sources of the project. I will rename the parameters and include a header file. Source file needs to be added to the build chain cause obviously it needs to be compiled and linked to the executable. Now let's include converted image in the main function and add it to the rendering. I'll set the X and Y positions to 0 with dimensions of 320 on 240 using 8 bits per pixel and a line data shift of 320. This value is used because the width is 320 pixels and each pixel occupies 1 byte. It will also require palette and flags. Flags I'll set to 0 for now. Let's compile and find some naming errors caused by letter casing. After fixing them, I'll run the project. On a low quality screen, the result looks magnificent. I don't see a lack of colors. The display smoothes it by overall poor quality. Not sure is it a good thing or a bad thing. I really look forward to replace these panels by IPS ones for the future videos once they arrive. Next I'll test the mirroring. Setting the horizontal mirroring flag should mirror the horses horizontally. Check, that works. Enabling both horizontal and vertical mirroring should flip the image on both axes. Check, both operations perform correctly. Now to check the performance, I'll render 4 full screen images simultaneously to gauge the performance cap. The result is still 47 FPS. This is very promising for parallax layers. Let's try 7. It drops FPS to 41 as a result. Let's bump the value to 9 sprites to get even worse results of 35 FPS. But there is a catch. Our data arrays defined as constants, which means that they will be stored inside the read-only memory of RP2040. That's how the linker works. And read-only memory is slow. In an actual game, the graphics and other data will be loaded into the RAM. I'll change the sprite definition to remove the const keyword, recompile and rerun the program. The result is back to 46 FPS. Most likely I'm just good at coding, or RP2040 is simply very powerful for a dollar price tag. I need to say that currently we are drawing without transparency. With transparency it will be a bit slower, but RP2040 should be able to handle at least 3 parallax layers. These layers of graphics move at different speeds relative to a camera to create the illusion of perspective, and Sega Mega Drive supported only 2 layers. Implementation of 4-bit, 2-bit sprites and masks present a new interesting problem. Imagine a 4-bit sprite in X position of -1. The higher part of the byte will be off-screen, while the lower half will be displayed. If the horizontal position is moved to 0, the data pointer cannot address a half byte, as memory operations require a full byte alignment. How to handle it? The easiest way is to extend our line screen buffers by 7 bytes on both sides. This will allow to safely draw off-screen data without additional checks. Pixels outside the visible range will never be sent to the screen. Why 7 bytes? In the worst case scenario, mask would have a position of -7, leaving only 1 pixel visible from an 8 pixel byte. Cropping for these sprite types requires trimming to the lowest possible position on X-axis with no more than 1 byte rendered off screen. Cropping requires removing of the higher part of the sprite data line with saving of the lower. For example, a mask position at -9 would be cropped to -1, aligning the visible section of the mask correctly. Each sprite type in this category requires its own filling line function. Also, their implementations may look similar, they differ enough in bit processing. When adding sprites, shifts are used to strip off the discarded part of the sprite data and adjust the data shift. In the filling function, I split each byte on pixels and write them to output in the same way as before. And as before, I use byte batching to render faster. For masks rendering, I'll use 2 colors instead of palette. Let's create an image of 16 colors to test our new functions. I'll pick an orange PNG. I like oranges. They have a strong bond with winter, at least in my head. Also, it is PNG already with transparency, which is good. I'll resize the image to 64 on 64. Now it's ready to be processed in Aseprite. In Aseprite, I'll create a color palette with 16 colors. Set up a new indexed image, load the palette and pass the orange into the canvas. Now orange looks fully retro with the nostalgia touch of Sega Mega Drive. I'll add the orange into the code. To do so, as always, I'll create a header file, rename everything and update the main code file to add 3 oranges in the main loop. The result looks fantastic, bright and very appetizing, but what I dislike about these oranges is they are static. Let's make it move since we are making graphics capabilities ready for game making. I'll define utility functions for sine and cosine used with degrees. These functions will ensure the values stay within the correct range and return results from pre-computed arrays. But how do we fill these arrays? There is a trick to do this. A real-life coding life hack. Open Chrome or any browser you're using. On any page, open the developer panel by pressing F12. Inside you will find the JavaScript console where you can enter JavaScript code. This is the fastest way, in my opinion, to generate lists of values. I'll multiply each value by 128 to avoid rounding them to 0 since we are working with integers. After generating and filling the mass arrays, let's jump back to the main file. I'll write a simple loop to display several sprites moving in a circular pattern. Each frame I increase the angle by 1 degree. Additionally, I'll align the sprites to rotate around the center of the screen, which is at 160 by 120 for the X and Y axes. Also, I'll subtract half the sprite size because sprite positions refer to their top left corners. And that's it. Let's take a look. The movement is flawless, it looks fantastic. Looks like a perfect New Year atmosphere since currently it's the start of December. Very relevant. Magical world of horses and oranges I dream to live in. What can we do with the masks? Obviously, some text rendering. I'll create header and source files for text functions. The header will define only 2 functions. One to get the letter sprites and another one to add a whole string to the rendering pipeline. Letters dimensions will be 8 by 12. I will copy the alphabet I created earlier into the file and modify the old function calls. Each bit of these bytes represents a pixel, and by looking at the code you can see the letter patterns. This way you can draw your letters by bit masks directly within the editor. In the main file I'll add 3 strings with different texts and simply call the string adding function. I also will pick different RGB 565 colors for each string. Let's do red, yellow and blue. Internally, the string adding function will simply call the add sprite mask function for each letter in the string. This approach isn't very efficient as we have a limited number of sprites available in the queue, but I'll discuss better approach later. Let's run the app to test it. And the text is completely unreadable with these colors. Letters are completely lost on this background. I changed the text color to white to make it readable. As you can see, texts and masks are extremely simple to use, nothing sophisticated. Later, in the far future, in galaxy far away, I may integrate more fonts into the system, allowing applications to choose from various options. Using fonts stored in the OS ROM would save RAM for game graphics. A bitmap font, including both upper and lowercase letters, would take up only a few kilobytes depending on the size of the letters. Still, it's a few kilobytes. All fonts will be custom-made bitmap fonts because running TTF fonts in the same way as Windows, Linux and macOS computers do on the fly might not be the best approach. Even so, it's technically implementable. It's possible to take Times New Roman and turn all the letters into bitmaps, but the resulting bitmaps would occupy more memory because they will be bigger. TTF font rasterization isn't optimized for memory savings, and the resulting bitmaps might look unattractive at low resolutions, but it could be simply fun to do in the future. As I mentioned before, matrix is a grid of sprites with the same properties, such as size and palette, organized with structured positions and a linear rendering process. When the matrix moves, all the sprites inside it move together, acting like a supersized sprite made of repeating tiles. If we use sprites with dimensions of 32 by 32 pixels and create a matrix with 100 sprites per line and 8 sprites per row, it will occupy around 800 bytes of memory plus tileset image and matrix technical information. This setup will create a level with the size of 10 screens. Tileset image is a grid of sprites itself and can be drawn in a sprite and exported the same way as we exported other images. In the rendering queue, matrix will occupy only one place, and that's very important. R12 matrix data is a structure used to describe the matrix. It includes all the necessary pointers, palette, sprite size and the overall matrix dimensions. Addition function of a matrix is simpler than the same function of a sprite, because matrix data already contains a lot of needed information. The fill function for a matrix will be more complicated than for a sprite. The reason is the limited space in the queue element structure, only 24 bytes. If any element of this C union exceeds 44 bytes, the entire union will be treated as a larger element, which will impact memory. In the fill function of matrix, I will calculate current line and Y shifts for all the sprites being rendered, since they share the same line in size. Next, I'll loop through all the horizontal sprites and call the rendering function for each one using the existing sprite fill functions. The matrix will be able to use any sprite type, whether 8-bit, 4-bit or masked, it doesn't matter. There are a lot of calculations involved, but there won't be many matrices. Additionally, matrices distribute sprites uniformly across the screen compared to regular sprites, which can sometimes be concentrated in a single line. Uniform spread benefits stable FPS. From my off-screen tests, I concluded that rendering 3 background layers along with sprites should work fine at 45 FPS. It's somewhat close to peak performance. Now, let's find some free tileset on the internet. Itch.io has a lot of options available for free. We are targeting something simple and isometric, with no more than 16 colors or close to that. I like this dungeon tileset made by 0x72. That's not a number, it's a name. From this list, I will need only 16 by 16 floor tiles. I'll open the image in Aseprite. Since it has more than 16 colors, I'll reduce the color palette to 60 and copy the tileset into an indexed canvas. The reduction might lose some details, but I didn't notice any difference. Let's export it. As always, I'll prepare the header file, rename everything appropriately, and we will be ready to add the matrix. Initially, I thought of creating a 4x4 matrix, but 60 pixel sprites are actually quite small, so in the near future I'll change it to 6x6. The values in the matrix data structure are pretty self-explanatory. If anything seems confusing, the structure itself will have clarifying comments in the code. Sprite list inline parameter equals equals 7 because the tile set is an 8x8 grid, but actually a 7x7 grid. The matrix data is stored as a one-dimensional array. The first 6 values represent the first line, since there are 6 sprites per line. The next 6 values represent the second line, and so on. I've aligned the values visually for better readability. I use 0 value sprites to make a hole in the matrix. Also, I'll move the 0 tile in the tileset image. I still want to be able to use it. So let's finally test how it looks. Well, 16x60 tiles are really small. I think 32x32 tiles would look better, especially on such a small screen, or maybe 24x24. Larger sprites reduce the number of variations you can fit into memory of RP2040. Let's take a quick look at how we can use matrices with text. Although the letters in the text source file might look separated from each other, they're actually aligned as a tile set. This allows us to create a matrix where each letter is represented as an 8x12 sprite with 1 bit per pixel. I'll set the sprite data to Z letter. Compiler places letters in the memory backwards, so after Z it places X. I'll create a simple 8-letter string that goes through the alphabet, but in reverse order. Let's see the result. Using matrices for text requires more preparation compared to using individual sprites. However, the advantage is that you can display really long, multi-line text efficiently, since the whole text is treated as one sprite in the rendering queue. This approach has a downside. You will only be able to use monospace fonts. Not like I'm planning to create letters with varying sizes. If your goal is to create a really well-looking text in your game, you might want to use letters with variable widths, maybe. It really depends on your creative vision. For example, VS Code uses a monospace font, because it's more convenient for coding, so monospace fonts are still widely used. That covers the basics of graphics rendering for RP2040 I wanted to present. However, we still need to fix input handling. Do you remember the new chip I installed on the board to consolidate all the button connections into a single serial line? Now it's time to write the code for that. The HC165 chip works simply. Toggles the load pin to reset the internal input register. The chip has an 8-bit register that captures the state of 8 input lines. Each pulse on the clock pin shifts the chip's internal register to the left. The bit output inside the chip always corresponds to the highest bit of the current register value. So the first bit we read is bit 7, followed by bit 6, down to bit 0. The chip can't operate at high frequencies, so I'll add NOP instructions to create a slight delay. This function won't be called often, probably once a frame, or twice, since future operating system will need to read input as well. I'm using a 2-byte value to store the button's state, because we might need more than 8 buttons one day. I feel that 8 buttons might won't be enough in the long run. To test the input, I'll draw an orange at a specific location when a button is pressed. I'll iterate through all 8 buttons. Since button's state is a mask, I can shift 1 by I to get the specific button. Button's enumeration consists of masks as well. Let's check the output. Everything looks fine, all buttons are registered properly. Pressing any combination of buttons works as expected. Thank you all for a lot of good words you have shared. Your support has motivated me greatly to continue this series and release this video earlier than I originally planned. Your likes, comments and subscriptions will motivate me further to make third episode appear sooner. I read and enjoy every single comment you leave. As always, description contains all the necessary links. The next episode will dive into SD cards and program loading, one of the trickiest parts of this development. Good luck with your own projects. I believe in you. See you in the next video. Bye.